Hello, my name is Bruce Crayenhoff, and today I'm making a screencast about trust region policy optimization. So this screencast is based on the paper, and this was a really important method, I'd say, in reinforcement learning. There's newer methods that use the main ideas of it, but the main idea is very important. And this is an important paper with some important people. Sergey Levine is a well-known person in reinforcement learning, and well, Michael Jordan, we all know about Michael Jordan, right? All right, so yeah, we'll be doing a quick overview. And then we'll go over some basic theory. We'll go over the approximation that makes TRPO, Trust Region Policy Optimization, work. We'll go over the algorithm, and then we'll discuss Proximal policy optimization, a similar algorithm. There's some other ones as well. And then I'll discuss a bit more about like why this works, what's great about this. All right. So what TRPO does is it implements constrained policy updates using the KL divergence. So KL divergence, you can control, well, with a constraint, you can control how different one policy is from another. So probabilistically, how different are certain actions from certain other actions. And some of the benefits of doing these constrained policy updates is that you tend to get monotonic improvement. So you don't need to worry so much about tuning hyperparameters. It doesn't go away, obviously, but this issue gets a lot better. As you may know, reinforcement learning can be kind of brittle, right? So this makes it less brittle. And this works for policies with very large numbers of parameters. And I'm not exactly clear why the number of parameters was an issue before. Why we could not just tune the hyperparameters to make it work, but anyways, now we have a solution to this as well. We can train huge models with TRPO. So it also covers this Vine method for sampling with a simulator, when you can take one path and then you can go back and take a different path. So this is only applicable when you have a simulator or when you know the model. And this doesn't seem to be the thing that has caught on and inspired lots of other work. So we won't be covering this. Because, yeah, it doesn't seem to have kind of stuck. Yeah, maybe it works in this particular case, but it's not some fantastic idea that everybody's building on. All right. So next we'll look at the extra return from an improved policy. So let's call that extra return delta eta. Hold on. So the extra return, delta eta, is just this expected value under our new policy of the discounted advantages under our old policy. All right. So here I've expanded it. So the new expected reward is the old expected reward plus the expectation under the new policy of this. Now, why does this make sense? Well, the advantage, so there'll be a number of questions like this. So pause the video right now and think about this, for a minute or two. Try and figure this out. And then, of course, I'm about to go over the answer. So the advantage tells you if you make a certain choice, how much extra return do you get because you made that choice. So here, so then we take the expectation over our new policy, so over all the new trajectories with their new expectations. And so then we add, on average, all the extra value that we get by making better choices. And yeah, so that's exactly why the new expected return is just the expectation over the new trajectories with the new actions, with the new probabilities of this value here. Yeah, cool. So now next we're going to make an approximation, which is, so this rho pi of s is kind of, it's on average how much you end up in state S. So I'm brushing over some details that we'll go into in a second. So this is on average how much we end up in that same state under the new policy, pi prime. And so we are going to be able to make this approximation and still get pretty good derivatives. So here's rho pi of s, and so I actually wrote it out as this expectation here. So this is an indicator function, and so we're basically just adding up whenever we're in that state. We're adding up the contributions. And so what that allows us to do is we can go from this format here, and we can say, okay, sometimes we might end up in the same state at a different path in our trajectory, right? So instead of adding up over all the trajectories, we can just add up over the states, and this takes into account kind of your probability of being in the trajectory, and it takes into account the probability of being at that state and the discounting gamma, right? It took it into account that as well, and so then so instead of adding up over t, we just take this and we can sum over all the different states. Cool. And then we sum over the actions, and so in our trajectory there's the probability of getting to a state and then the probability of taking a certain action given that you're in that state, right? So we have that probability of taking that action separately here, because that of course depends on the action that you actually take, right? Cool. So this is the new expected reward, and now we're going to make our approximation that, well, this is going to be approximately this. Now this will be valid to first order. Now it's not valid to first order then that this is equal to this in first order. It's that our approximation for this will be valid to first order when here we plug in the original state they're kind of like state probabilities. They're not actually probabilities. So let's understand why that is. Well, first of all, we'll understand why that's a useful approximation. So now our expected increase in average return is approximately this. Okay? And so I've written it here. So this now is just basically an expectation over the old state distributions and the old actions that you take in each state under the old policy. And then we need this factor because, well, it was supposed to be under the new policy, so we need this factor here. And we have the advantages, again, under the old policy. Cool. So first of all, why is this such a useful approximation? Why is this a useful form of the equation? So pause the video again. And the answer is that here, this is just sampling under the old policy. So we can do a bunch of sampling under the old policy, and then we're just going to be able to reuse that for a while, right? And these advantages were also calculated under the old policy, so we don't need to keep updating that while we're calculating a new policy pi prime. We don't need to update the advantages because that's just the advantages under the old policy. So all we really need is, well, we need to calculate for each action using the samples we've already collected. We just calculate the ratio of the policy under the old and new policies. So yeah, this is fairly simple. So then we can just, using the same data, we can just keep crunching this a few times for a few kind of epochs over those samples. Yeah, so I would call this like a near policy algorithm, right? So in order for this approximation to be good, in order for this approximation to be fairly good, we can't be too far off policy, but we can be a bit off policy. Okay, and we'll go over why more later. And then we can do repeated updates using the trajectories we already collected, which is pretty fantastic. So we haven't gotten into TRPO yet, but we've gotten into the approximation, which is part of what we use for TRPO. Cool. So now let's go into why this approximation is valid. Well, actually, see if you can figure it out. And it has to do with the expected value over all the actions of the advantage. So pause it, see if you can figure it out. So why is this valid? So let's kind of do some linear approximations. So pi prime is the original policy pi plus some small change, right? And this similarly will be the new kind of state distribution, will be the old state distribution plus some small change, and this small change is due to the change in policy as well. So this small change is also linear in the change in policy. Cool. So let's just consider this sum here. So this sum would be the same as that sum plus these small changes, right? Now, remember the sum over, hold on. Right. Yeah. So this sum over the old policy of this is just going to be 0, right? Because that's the advantage. It's on average how good each action is compared to the average, right? So if you just average all over them, you get 0. Okay, so that term becomes 0, and we're just left with this remaining term. So we can see that this sum here is it has a delta pi in it, right? So as long as our policy change is fairly small, this whole term will be fairly small. Cool. Very cool. So now we're going to look at the entire, improvement in the expected return. And so we've got our old equation. We're going to plug in our estimates for these. So that's what we've done here. And this just became that, like above. We can multiply this out. So we get this term, which is the term we're used to, and we get this term. And you see this term, it has, well, this is fairly small, as long as our policy change is small, and this is also fairly small. And so you get this, like a fairly small term squared. And so this term is just way smaller than this term, as long as our policy changes are fairly small, which is why approximately we can just say this is about 0, or we could estimate the kind of error from that more accurately if we wanted to, but it's approximately 0. And so we're left with this. So that's pretty cool. As long as our policy changes are fairly small, we can use the old trajectories, and all we're going to have to do is we're going to have to do that. We're going to have to do that correction, because this term, well, this is non-zero, right? So we're going to need, where was it? We're going to need that term. Yeah. Yeah, we omitted the last term because it was second order in the change in the policy. So here we've replaced this row pi prime with row pi, and that was approximately correct. Why couldn't we change this with just pi? Well, I mean, pause it and think about that. So the answer is, so the sum over all of these is approximately 0, because the sum of advantages, sum over all the actions of the advantages is 0, and this is approximately the same. So that's why that's approximately 0. Right. Yeah, so the sum over those is 0. but each individual advantage is not 0, right? And each individual advantage is multiplied by a different pi prime. Hold on, I need to think about that more. Yeah, I mean, ultimately it comes back to these infinitesimal things. So this whole thing, because this is a bit different, this will be approximately what it was with pi, but with a small change. And so we can take that small change times this, which is not small, and that gives us, a first order term. But if we take something small times this is a first order, that's first order, so then we get a second order term. So really it's the same thing. That might not have been a good question. Okay, so TRPO uses this approximation and constrains the size of steps that we take so that the approximation stays valid. So let's look over the algorithm roughly. So I'm not going into all the gory mathematical details, just giving you the idea. Cool. So repeatedly, what we do is we collect a sample batch with our policy pi before we update it. Okay, so this is, I don't know, maybe this is 2,000 or maybe it's 2 million, depending on kind of the scale of our algorithm that we're performing. And then we optimize some new policy pi prime, and we do this for a few epochs of where we sample training batches. So we've got our 2,000 samples under the old policy, and then maybe we just sample 20 at a time as training batches. So the training batches might be 20, where we're sampling those training batches from the sample batch of 2,000. And so then we just use this, and so we're trying to maximize this. So we just do back propagation. We probably have a neural network, right? To optimize our policy pi prime here, which only occurs here. Everything else, this is how we sampled, so these don't come into the optimization directly. They came into it that's how we sampled the data. And so really we're just trying to optimize this with respect to this pi prime. And so we take derivatives, back propagation, and we optimize our pi prime. However, we want to make sure that this remains valid, right? And so we don't want to go too far away from the old policy. And a way to ensure that is to ensure that the KL divergence between the policies, so between the trajectories they generate, stays less than some small number, where epsilon might be something like about 2%, right? So on average, you don't go more than 2% away from where you were. And there's a bunch of tricky math for how to do this efficiently, and I have actually skipped that myself because there's other ways that work quite well, which achieve the same ends. But basically, we enforce this constraint as well and optimize this. And then after a few epochs over the sampling batches, right, then our new policy becomes pi prime, and we repeat, right? Get another sample batch, train on it again. So that's at a high level, that's the TRPO algorithm. Now, there's some similar algorithms which are more commonly used nowadays, as far as I know. And the most common one is called PPO. So PPO, whoops, this is proximal policy gradient. So proximal refers to, again, we don't want the policies to differ too much so that our approximation stays valid. So this is proximal policy gradient. OpenAI is using it all the time. And yeah, so it kind of seems to be the successor to TRPO that was inspired by TRPO. So instead of doing a constraint, what it does is this is the thing we're trying to maximize, and so it just clips it. So if you go too far away from, if you go beyond the 2%, then you stop getting any reward. You can still get punishment, but you stop getting any reward for, changing pi prime more in that direction. And so this, by effectively changing the loss function, right? We're changing what we're trying to optimize. We're not constraining it, but pi prime kind of has no more incentive to go beyond 2% away from the original policy. And so we don't have to worry about a constraint. This becomes very simple and in practice works very well. Yeah, cool. So I just want to go over basically how these algorithms work again and what's so great about them. So they're basically doing something like batch gradient descent, where here for these batches I'm thinking of the sample batch. Except the magnitude of the update in policy space is controlled so that the approximation stays valid. And another benefit of this is things won't tend to go horribly wrong. If you're just 2% more or less likely to take each action, probably you won't go from a good policy to a horrible policy really quickly, right? Now, so that gives us a degree of control in policy space. Whereas when we're updating parameters, sometimes, you make a small change in parameter space and the policy barely changes at all. You make another small change and all of a sudden the policy changes by a lot, right? Because, derivatives can change. So this gives us more control in policy space, which is what actually affects how our algorithm will perform. So I think this is part of what makes TRPO and PPO more reliable. We don't have to be really careful about hyperparameters and yeah. Now, so that controls the magnitude of your updates. Now, so long as we collect enough data in each sample batch, then we should get the direction of our update roughly correct. And since we train from multiple epochs of the same sample batch, this actually allows us to do second order and kind of higher order updates with on the same sample batch of data. So this will work well for deep models like neural networks, where these nonlinearities are really part of what make it work. So we can be more efficient in using data than with a purely on policy algorithm. Yeah. So what are the benefits? Tend to get monotonic improvement because we have that control in policy space. The updates usually increase the objective, or at most decrease it by a little. It could decrease it by a little, and there's a few reasons why. First of all, we are making an approximation, right? So there's those second order effects. The approximation is like a first order approximation. So we're ignoring second order effects, which possibly could make things worse, right? And second of all, our sampling could be imperfect. So given this, if TRPO or PPO isn't converging to a good solution, what could you possibly do to make it work? What might make it work better? So pause it. So if you increase the sample batch size, that will help you get your direction better. So when OpenAI is using this on the game Dota, where they're training 5 heroes to work together to play that game, a fairly challenging task, they want to be pretty sure they get the direction right. And so what they do is they collect about 1 million, spread out over a bunch of computers. They collect like 1 million samples, and then they do their updating. So bigger sample batches will help you get your direction more correct. And then to deal with the second order effects, you can make your KL divergence constraint tighter, right? So that becomes more accurate. Presumably, as you get closer to the optimum, then you should probably make your constraint tighter, so that you make sure that you don't mess yourself up too much with these second order effects. Yeah, and it might be good to increase the sample batch size as well as you near equilibrium. And of course, there's some things like if you're training, if your learning rate is too high, you could be ineffective at training in general. I mean, there's all the ordinary things which are also apply to just plain supervised learning, but we're pretty good at supervised learning now. So these are the more reinforcement learning specific things that might help TRPO converge. All right, thank you for watching.